In this video, we're going to look at Taylor's series, which are just the infinite series of the polynomials that we saw in the last video. So in the last video, we had a bunch of different terms, and so the zeroth Taylor polynomial would be just the zero term. The first Taylor polynomial would be the zeroth and first term. Second would be the zero, first, and second, etc., etc. And if you do this out to infinity, that's where we have the Taylor series. So the Taylor series is the Taylor polynomial with infinite terms, as I just said. So if it's fewer than infinite, we'd call it the first, second, third, fourth, fifth, etc. Taylor polynomial, which is just up to n equals whatever number you are. So if it's the 10th Taylor polynomial, that would be up to n equals 10. So from n equals 0 to n equals 10. The Maclaurin series here is a special name for a Taylor series that's centered at x equals 0. So if a is 0, in other words, a is 0. So if this really shouldn't be x, it should just be a equals 0. So if a is 0, it's also called the Maclaurin series, but the AP test appears to be moving away from using that term. It is technically still in the curriculum, but usually what they say now is just a Taylor series centered at 0. But it is useful to be exposed to this because you might see it in other classes or in other material. But it's exactly the same equation, exactly the same stuff, just instead of having a be an arbitrary number, it's specifically for a equals 0. So the Taylor and Maclaurin series will exactly match a function if that infinite number of terms is used. So I talked about this in the last video. This is a perfect match for the function. And this is useful because, as we said, it's often easier to work with polynomials than it is to integrals. So if you remember, with polynomials, if you want to integrate or derive, it's straight up just, power rule. If you want to integrate or derive some complex sine function, then you've got to do chain rule and all those other things. So if we can approximate it with a polynomial or write the infinite series, then we can work with that polynomial as opposed to some complex function. So even if we're not using an infinite number of terms, though, an approximation might be close enough. So even if you don't go out to an infinite number of terms, especially with computers these days, a 100-term polynomial might be better for computing than a nice simple like f of x is equal to cosine of x. Because if you want to do this, you gotta, to approximate values, you gotta plug things in and work with it. But if we have a polynomial, even if it's a really long one, that might be easier to compute with. Oh, that's a duplicate slide in there, so let's go into our example. Find the Taylor series centered at x equals 1 for the function f of x equals 1 over x squared. Present your answer by writing the first three non-zero terms and the general term. So if we remember, the kind of way that we expand out the Taylor series is we're going to always start at 0, we're going to go to infinity, and then we're going to have the nth derivative at a over n factorial times x minus a to the n. So this is our series sigma notation. So now we need to find the first couple of terms. So for n equals 0, let's write out some of our derivatives. That'll help us. So f of x equals 1 over x squared. F prime of x is equal to the derivative of that is going to be, this is also, I'm going to write it as x equals -2 because that's going to be easier to work with. Derivative will be -2x to the -3. F double prime of x is equal to 6x to the -4. F triple prime, I don't know if I'll need this, but I'm just going to write it so I have it. It's going to be negative 24x to the negative 5th. So we've got those written down. N equals 0 says that we have the 0th derivative of f of x, so that will be 1 over a squared, which we're centered at x equals 1. So 1 over 1 squared divided by 1 factorial times x minus 1 to the 0th power. So, sorry, that should be 0 factorial. So it's the nth derivative of f of x at a. So the nth derivative would be the 0th derivative, which is just the original function. So 1 over 1 squared divided by 0 factorial times x minus 1 to the 0th. This is 1 divided by 1 divided by 1, so that's all 1. X minus 1 to the 0th is 1, so this term is 1. So that's our first non-zero term. Our second non-zero term is going to be n equals 1. So this is going to be negative 2 times 1 to the negative 3rd divided by 1 factorial times x minus 1 to the 1st. Negative 2 times 1 to the negative 3rd is just negative 2. 1 factorial is 1, so we get negative 2 times x minus 1. So that's our second non-zero term. Our third non-zero term is going to be f double prime of x, so that will be 6 times 1 to the negative 4th over, in this case, it is n, so 2 factorial times x minus 1 to the 2nd, and that will give us 6 divided by 2 factorial, which is just 3, times x minus 1 to the 2nd. And now we have to get a little clever to figure out our nth term. So these are our first non-zero terms. So we're going to write 1 plus negative 2 times x minus 1 plus 3 times x minus 1 squared plus some unknown, and then we'll have our nth term, and then infinite terms after that. Now you might already think you notice a pattern. Let's write out a couple more terms just to start checking with that. So n equals 3 is going to be negative 24 times 1 to the negative 5th over 3 factorial times x minus 1 to the 3rd. And that will be 3 factorial is 6, so that will be negative 4 x minus 1 to the 3rd. So you might notice the pattern that our coefficient is alternating but increasing by 1 each time, and our exponent is increasing by 1 each time. Our coefficient starts at 1 and our exponent starts at 0. And this makes sense from what we're seeing here is our coefficient on these derivatives are increasing by factorials. So I have 1 factorial, 2 factorial, 3 factorial, 4 factorial, and then I'd have 5 factorial because I'm always doing the product or the power rule and I'm bringing the power down. And because the powers are negative, they're increasing, right? They're becoming a bigger negative number, or a more negative number each time. So in other words, each time I multiply by the next integer up. So that means in the numerator, I'm going to, or in the coefficient of this, I'm going to have n factorial. The denominator is always 1 less factorial. So actually the numerator should be n plus 1 factorial. So let me write that properly. And this is just because we started with 1 factorial on the 0th term, and in the denominator we have n factorial, which means it simplifies to just n plus 1. So we'd have negative 1 to the n plus 1 because we see this alternating fact. And then I'm going to need more space here. And then we have n plus 1, which we see. And then we have x minus 1 to the n, because that's what we see for these terms here. N equals 1, we have x minus 1 to the 1st power. So this right here is the general term, -1 to the n plus 1. Actually, it should just be -1 to the n now that I'm looking back at it, because our first term is negative. So this is where it is just a bit of logic and kind of figuring things out and making sense of it. But this right here is our general term, and then we have our first three non-zero terms. So this right here is going to be equal to 1 over x squared. So if you graph 1 over x squared and you graph this expression with the infinite terms, they will be exactly equal. We'll jump into the Lagrange error bound in the next video just so we have some more time, but I want to kind of preview that here.